This is R Tejeswar, BT23CMP088, and this is my transfer phenomena assignment video content creation. The topic I have chosen is diffusion in cylindrical coordinates. So we'll be dealing with mass transfer across a cylindrical shell, which we have assumed to be our differential element. So in our first question, a chemical plant, a hollow cylindrical pipe made of porous material, is used to transport a gas mixture. Component A, a valuable gas, desirable gas, slowly diffuses radially outward through the pipe wall into the surroundings. The pipe has an inner radius R1 and outer radius R2 and operates under steady state isothermal and constant pressure conditions. These assumptions are very important. The concentration of A at inner surface is maintained at XA1, while at the outer surface it is XA2 due to environmental exposure. We assume one-dimensional Radial diffusion only in ideal gas behavior, and we use a differential shell balance along with fixed law of mass diffusion in cylindrical coordinates to derive an expression for the radial molar flux of A, which is our goal. The diagram basically looks like this. This cylinder right here, this cylindrical shell is our differential element of thickness delta R. The flux coming into it is represented by NAR at R. The flux leaving the shell is represented by NAR R plus delta R. The length of the cylinder is L, as we know, and the inner and outer radii of the cylinder are represented by R1 and R2. Now, in the assumptions, we have assumed one-dimensional radial diffusion. So we know that XA is only a function of R, which is the radius of the cylinder. So the only non-zero molar flux component is NAR and is given by the formula minus C dAB dXA by dR. But C is a constant, dAB is the diffusivity of desirable gas A in B, and dXA by dR is the concentration gradient of component A. Now if we take a cylindrical differential volume element of thickness delta R as I have shown in the diagram, the equation of continuity looks like this. This is the mass in and this is the mass out of the cylindrical shell that we have assumed to be our differential volume element. The difference is 0 as there is no consumption or generation. Now we divide this equation by delta R and we take limit delta R tends to 0. Now this is basically the definition of derivative. So this becomes the derivative of ANAR with respect to R, which equates to 0. We know that flux into area gives us rate, and we also know that ANAR, which is the mass coming into the shell, is equal to NA, which is the molar rate of transfer. Here as I have written, NA is equal to rate of mass transfer. Now the area perpendicular to the mass flux direction is 2 pi RL. Now the mass flux direction is radially outward, so the area perpendicular to it will be 2 pi whatever radius R into L. Now we sub the value of area into the equation in here, this continuity equation. We also sub the value of NAR into this equation to get this integral right here. Now we apply the boundary condition at R is equal to R1, X is equal to X1, and at R is equal to R2, X is equal to X2. Can be confirmed here. At this point, XA, the mole fraction component A is XA1. At this point, the mole fraction is XA2. Now we find the final results. Assuming constant DAB, this DAB does not change with time or radius. The molar transfer rate, the rate of mass transfer, comes out to be this when we apply these boundary conditions into this equation. The concentration distribution, the profile, comes out to be this. Moving on to the second question. Consider steady state one-dimensional radial diffusion of species A through a hollow cylindrical shell of inner radius R1 and outer radius R2. The system is isothermal and at constant pressure. So basically the same scenario as the first question, but here we need to start from the equation of change for species A in cylindrical coordinates and simplify the general species continuity equation under the given assumptions. Then we need to obtain the governing differential equation for radial diffusion of component A and integrate that equation using boundary conditions at R is equal to R1 and R is equal to R2. Then at last we need to derive an expression for the molar flux and total molar flow rate of A through the cylindrical one. The assumptions remain same with no bulk flow, meaning velocity is 0 as there is little to very less convective transfer. We are assuming steady state, so dCA by dt is equal to 0. dB and C are already constant like the last scenario. There is no reaction in the wall, so RA is equal to 0. We start from equation of change for species A in cylindrical coordinates. Here to some glitch it's not showing, but let me show you. As you can see here, we start from the equation of change for species A in cylindrical coordinates, which is dou CA by dou T plus del operator into CAV, where V is characteristic velocity, is equal to delta into DAB delta CA plus R. Now in here, due to steady state, dou CA by dou T is 0, and as there is no bulk motion, V becomes 0, and there is no reaction in wall, so RA becomes 0. The only remaining term is del into DAB del CA, which will be equal to 0. So if we factor in the assumptions, we get this. And as C and DAB are constant, this equation becomes del square CA is equal to 0. Now in cylindrical coordinates, when we expand del square CA, we get 1 by R dr, R dCA by dr, plus 1 by R square, dou square CA by dou theta square plus dou square CA by dou Z square is equal to 0. But as we know, as we have stated in the assumption over here, we assumed one-dimensional radial diffusion only, which means the mass transfer happens only with respect to R and there is no mass transfer in the theta or Z directions. So both dou CA by dou theta and dou CA by dou Z become 0, and the final governing equation becomes 1 by R d by dr of R dCA by dr is equal to 0. Now if we integral on both sides, if we take integral on both sides, this stays 0, and we get R dXA by dr is equal to C1. This becomes the first constant of integration. Now when we integrate again, we get XA is equal to C1 ln R plus C2, which is the second constant of integration. Now we apply boundary conditions that are the same as last scenario. At R is equal to R1, X is equal to XA1, and at R is equal to R2, X is equal to XA2. Now when we apply these boundary conditions in this equation, we get two similar equations in the form of XA1 is equal to C1 ln R1 plus C2, XA2 is equal to C1 ln R2 plus C2. Now when we subtract 1 from 2, XA2 minus XA1 is equal to C1 ln of R2 minus R2 by R1. Now when you take ln R2 by R1 to that side, C1 we get the value of C1. Now we get the value of C2 from here. Let's bring the value of C1 and C2 into the general equation of XA, this equation right here, you get something like this. Now, in this equation, we take C1 common, so we get ln R minus ln R1, which becomes ln R by R1, and then we input the value of C1, which is this XA2 by XA1 by ln R2 by R1. Now, molar flux NA is equal to minus C dAB by dXA by dR, which we know. And now in this we input the value of we input the value of XA in dXA by dR. So we basically differentiate this with respect to R. Now this becomes 0, and then this becomes this as minus C dAB by R when same. Now molar flow rate denoted by Na equal to molar flux into area, as we know, and the area, perpendicular area to the direction of mass transfer is 2 pi R. So we get this as the final result. Moving on to the numerical, a hollow iron cylinder of length 100 mm has inner radius 4.3 mm and outer radius 5.7 mm. Carbon diffuses radially outward through the cylinder wall under steady state conditions. The total amount of carbon transferred is 3.6 into 10 power minus 3 kg over 100 hours. Carbon concentration varies with radius and the diffusion coefficient DAB using steady state cylindrical diffusion equation. Now, got to mention the data. There is another piece of data which will be mentioned. So yes, we can resume now as we have this data, which gives the relationship between carbon concentration as weight percentage versus radius. So we have the inner and outer radius as the length of the cylinder, and the expression for molar rate of mass transfer we have already derived in previous scenario. The same goes for diffusivity. Now, as we have been given, mass transferred is 3.6 milligrams in a total time of 100 hours, which amounts to 3.6 into 10 power seconds. Molecular mass of carbon is 12 kg per kilogram. So we put this into basic formula for Na, which is mass transferred per molecular mass. This is the moles transfer in this type. Now when we divide the moles transfer per the time, we get the molar transfer rate, which comes out to be 8.83 to 10 power minus 10 kilomole per second. Now when we plug this into the initial equation for diffusivity right here, we get an expression for DAB in terms of the concentration difference, which is 3.74 into 10 power minus 10 by CA1 minus CA2. Now, assuming CA1 versus LNR is linear, at R1, which is endpoint 4.49, the weight percentage is 1.42, and at 5.53, weight percentage is 0.2. We have taken the endpoint, which is an approximation, which is very close approximation. We will not get much of error. So we compute the slope. Del LNR is 1.74 minus 1.53, which is the change in percentage is 1.04%. The slope comes out to be this by this 2 by 1, which gives us minus 5.43. CA1 minus CA2 is equal to m ln R2 by R1, and we plug the value of m ln R2 and ln R1. We get the value of CA1 minus CA2 as 0.0153, and this we can enter the expression for DAB in terms of CA1 and CA2 right here to get the final diffusivity to come out as 3.7 into 10 power minus 11 meters square per second. Final question, fourth and final question. Hydrogen gas at 2 atm and 27 degrees Celsius is flowing in a neoprene tube 3 mm inside diameter and 11 mm outside diameter. Calculate the leakage of hydrogen through a tube 1 meter long in kg mole hydrogen per second at steady state. we have been given that pressure inside is 2 atm, and we have assumed pressure outside to be 0 atm. Temperature is 300 Kelvin and 27 degrees Celsius. Length is 1 meter. Inner diameter and outer diameter have been given. So we can find inner radius and outer radius. The governing equation which we have derived in the first question remains the same. We are assuming the concentration of hydrogen outside to be negligible, which means Ca2 will be 0. Hydrogen in neoprene is the data for diffusivity and solubility is hydrogen neoprene standard data at 300 Kelvin. Diffusivity comes out to be 1.2 to 10 power minus 10 and solubility is 2.4 to 10 power minus. Now we know that to obtain concentration from solubility we need to multiply it with pressure. Pressure is given as 2 atm. We multiply it and find the concentration which is Ca1 to be 4.8 into 10 power minus 3. Now as we have assumed Ca2 to be 0, we have N, we have DAB, we have R2, we have R1, we have Ca1, we have Ca2. Now we can find molar rate of transfer. That is the leakage of H2. Yes. So we can find the rate of molar transfer of mass of hydrogen through the neoprene, which comes out to be 2.78 into 10 power minus 12 kilomole per meter. Thank you.